Should I try to... Yeah. This seems doesn't work. Yeah. Oh, I guess it's not a plug-in crackle. Okay, I think I'm ready. Yeah, I'm ready.
All right. Our next speaker is Zhou from Purdue.
Yeah. Hello, everyone. My name is Zhou from Purdue University. It's glad to introduce our work, trace-guided synthesis of effectful test generators. This is joint work with Ankush Desai, Benjamin Delaware, and Suresh Jagannathan. Our work is about property-based testing. Let me first give you some basic intuition. Assume that you want to test a functional program, but you don't want to write down the unit test manually. So you can take a test generator, generate test inputs for you, and you execute the program, gets outputs, and then you combine both of them to what they call the executable property, which defines what it means about the functional correctness of the program. If you find a violation, it means that you do detect the bug. Otherwise, you can just do it, retry it, ask the test generator provide another test input, and do that once again. Now the question is that how can we make this whole procedure more efficient? One idea of the property-based testing is that the test generator needs to focus on do some smart exploration, focus on some input space more likely to trigger the potential bug. And that smart exploration needs some guidance provided by the human. For example, if you want to test the insert function, which take a tree and element, then return another tree. The property is if the input tree is a binary search tree, or BST, then output tree should also be a BST. Look at this test input. You will find this tree is not even a BST. So that will be directly rejected by the precondition of the property. So explore this test inputs is totally useless. Then one kind of guidance provided by the human need to contain some basic correctness to avoid this bad input. Here's another kind of input. We believe that is good because it has somehow smaller depths of the tree. User probably have some domain knowledge that believe a smaller depth of the tree were more likely to trigger the bug. So another kind of guidance is a search bias. However, the things are quite different when you do the PBT with effects. Now we don't have a functional program, but we have an effectful system, just like a stateful library have a shared internal state, and that also provide a set of APIs. So the test generator don't provide a test input, but do interaction with the effectful system. For example, where there's input events and output events. That is some invocation of the APIs. Now the question is that how can user easily control this kind of interaction between the test generator and the effectful system, but still do the smart exploration with guidance? Let's take a concrete example. Assume the system we consider is a system that can parsing, type checking, and do the interpretation over some language terms. Look at this. The test generator can using this parsing API to construct AST consecutively, and also can do type check and evaluation. The point here is that in the effectful system, the test input is not a data type or not an AST, but some traces of events. So the language term we consider in this example is simply type lambda calculus, STLC, with the Bayesian index. So people probably more familiar with the STLC term with the named variable like this. You have x and y, which actually refer to the previous STLC abstraction bindings. However, that is not closed under this alpha renaming. You have lots of variants. So the Delaware index can unify them using this, where we don't use a variable name, but we use the index. The 0 index refers out the closest abstraction, and 1 index refers as the outer abstraction. So the Delaware index does the unification, but also makes it tricky to implement a correct interpreter within it. So concretely, we want to test the interpreter API in the system, and the property is the well-typed STLC term cannot get stuck. So the potential bug is the interpreter probably use an incorrect substitution. Here's the STLC term, and you can imagine the test generator send the input event, say eval, and the evaluation gets stuck. That is ill form because index 1 tries to refer the outer abstraction, but there's not an outer abstraction. The point here is that the only STLC term with a very specific shape can trigger this bug. You need to have application, otherwise this substitution will not happen. And you should have the non-zero Delaware index. And also to make sure the non-zero Delaware index, you need to have the nested function. So how can we construct such kind of input? For Effectful systems, still we don't directly provide the AST. In order to construct this nested function, the test generator do interaction with the system. Assume the system originally stored AST with unknown node, and the test generator say, I want an abstraction with net-to-net type. And the system then return the depth 1, that is the depth of the nested function, and transfer to another state. You can see this ASTR change, and you can say the test generator want to another abstraction, and then want to abstract application. You do that consecutively. That's the way you construct this AST in an interactive style. So the question is that, how can we do this directly property-based testing? Or more concretely, how can user easily control this kind of interaction? So the first challenge is that people need to specify this basic correctness and searching bias for actually the trace of events, not the data type. Assume this is a trace of events, and people need to specify like well-typeness, and that need to exist in nested function application. The second challenge is how can we ensure a test generator indeed do this text exploration following the guidance provided by the human. This kind of a correct test generator are hard to write and also deliver more user burden. So we try to do that better. We actually try to synthesize the correct test generator that is correct by construction. Let's move on to the first challenge about the specification. We introduce a notion, what we call the local specification. The global specification is exactly the property you want to test against, and it encodes some basic correctness, like well-typeness. The local specification is a spec for each API or each event. For the API eval, it means that in order to trigger the dangerous substitution, there at least need to have an application. And we also have the specification for ABS or the var, that encoding some Delaware index semantics or well-typeness. So the whole workflow is that the user provides a global property and local specification. Our synthesizer, we call it Cusot, synthesizes this generator for user. The point here is that the user don't need to provide potentially complex search bias, where our synthesizer can infer it from this local specification global property, because our local specification encodes the event dependency. So how can we specify the event dependency? We introduce a specification language called U-heads. The heads is the previous works, is a refinement type system equipped with a pre and post condition in a Horror style. It's have a parameter type and return type, but also have P and Q. Like Horror logic, but it's quantified over traces. We want to highlight that the P and Q are not just regular expression, but it's a symbolic one, which is rich enough to express more complex constraint, like the arithmetic relation in the divergent index. And this specification, or approximate, describes the safe behavior of an API. For our setting, we take an underapproximation variant of the hat, where it describes a subset where a test generator must be covered. And there's also have a must-del semantics. It say, to generate the trace satisfies the post-condition Q, there must exist trace in the precondition P. I can give you an example of the U-hats. For example, the var, you can see have a pre and post condition like this. It's actually have an event dependency. The var actually refer previous abstraction in the ith outer level. So this one is correct, but this one is not, because this index 1 doesn't have any outer abstraction here. So also have a must-del semantics. It say, to get a non-zero index, there must exist a previous nested function abstraction. Let's move on to the second challenge about the soundness. We first introduced a DSL for our input generators. In order to make sure this test exploration provide a correct divergent index, our test generator need to actually observe the output events from the system, like the depths. We store that as a variable d, and we have an assertion. We assert this depth as a valid depth, otherwise we even detect an error in this parser API. And we have random generator and assume, which can make sure this new index are valid divergent index. The point here is that our language is a solver-aided one, so we can use this as some store like this array to deal with the assert and assume. After that, we can safely call this var to generate the input event and send that to the system. More interestingly, our DSL have recursion and non-determinist choice. This is sufficient enough for us generator to explore a family of interesting traces following the guidance. So our type soundness says the synthesis test generator should be consistent with both global property and local U-hats. Assume that is a trace generated by our synthesizer generator, and the whole trace need to represent some well-typed STLC term. And if you focus on one specific event, which divides the trace as a prefix and postfix, this is consistent with the P and Q within the U-hat of a var. Let's move on to challenge about the synthesis. We derive a type-guided synthesis algorithm where is a correct by construction. So how can we guarantee the synthesis generator are consistent with the global property? We take the global property and actually convert it into a candidate generator. That's exactly a program in our DSL, but with some holes. You can see a well-typed program need to be either be basic type or arrow type. So you can see there are two branches. And the next challenge is that how can we make sure that it's consistent with the local specification? Let's take a look at the first branch, for example. We actually try to fill the events into the program holes. So our algorithm have a refinement loop to fill this program hole consecutively with events. For example, like this, you can find this is not quite right because we said that the var need to refer some abstraction, which is missing. What we can do, we take the U-hats of the var, which have to encode the event dependency in the precondition automaton. And you can merge this U-hats and the candidate generator to get a new candidate generator where this ABS actually fill into this program hole. You do that consecutively and until all the events are consistent with this local U-hats. So that is how we make sure that it's a correct by construction. Let's move on to the evaluation. The first research question we care about is expressiveness. Our tool Kuso actually can target it to multiple backends. One backend we consider is OCaml backend, which has the QChat as a property-based testing framework. In this backend, we focus on the sequential program, but also in a very diverse domain, like effectful data structure, in serialized data like STLC, and even database. You can see all these are sequential program, but the data sets even have some concurrency constraint. Another backend we consider is P language, is automatic reasoning language for distributed model. So this is a quite different setting. It's not sequential program, but actually we have a set of nodes in the distributed system, and each node are implemented as a state machine. This state machine can send message and receive messages. So for this benchmark, we select the well-known distributed protocols, and all of our benchmarks are selected by the prior works. You can see they are quite diverse. We're also curious about the user input. The user need to provide additional U-heads. For each U-heads, we actually count the complexity by how many data dependency constraints encoded in these U-heads. In average, each U-head user need to provide 3 constraints. This means that Kusu doesn't require a lot of user inputs. And the synthesis overhead is also low. The average synthesis time is less than 3 seconds, and the maximum time is less than 3 minutes. And we also achieve a good performance. We count the bug detection rate. For 2 groups of benchmarks, our synthesized generator by Kusu can detect 100% bugs, although our baselines, the random generator and the human random generator, are relatively low. We want to point out that the human random generator are well designed. They actually encode all this guidance manually. And within all the case human generator can find a bug, our synthesized generator can do that much more faster. Okay, let's move on to the summarization. Our tool Kusu allow user to encode the task exploration guidance into our specification language U-heads that can specify event dependency with the master semantics. And we introduced a DSL, which is statically typed solver 80-1 for the Effectful generator that's supporting very diverse domain. And we'll have a type-guided synthesis algorithm, which can leverage the basic correctness and the searching bias from the global property and local U-heads. Thank you.
All right, we have some time for questions.
Hi, Harry Goldstein, University at Buffalo. Thanks for your talk, very nice. I'm wondering, you talked a bit about effectful programs, but then you were talking about STLC, which I don't usually think of as particularly effectful. So can you talk me through like where the effectfulness is and why this is like what makes this problem very distinct from the problem of just generating STLC terms normally?
Yeah, so if I understand your question correctly, is that you think this SLC is not be traditionally treated as an effective one, right? The thing here is that in our setting, as what we show in this slides, we don't directly provide this EST, but EST actually some stored in the state of the system. And you can like do that like the objective-oriented language that you can construct it, mutate it within the different interaction between the test generator. I agree, you probably have a different kind of a style to encode the whole progress. For example, you can directly generate this EST. But our targeting is serialize the data. Like you indeed have a parser, right? You can imagine the parser take a sequence of a token, and the order of the token are quite important. So it's not just EST. Does that answer your question?
Hi, thank you for the talk. I'm a PhD student from Zhou Boulder. I have a question on, so if the user need to write the U-head for the verification process, then if it fails due to some like with our own specification, do you give any some like counterexamples or feedback to users?
Yes. So if I understand correctly, you mean that when the user provides the wrong U-heads, what happens? So there's several kind of error we can define. One error is that the U has is a totally make there's no existing synthesizer exists. It's probably self-conflict. In that case, our synthesizer will detect it, find there's U hat are conflict with each other, and we will provide a concrete instance to it. Another kind of wrong U hat is that, for example, our U has assumed this parser have a debugging index within the system, but it's a totally don't have such a guarantee. So the U has didn't really align to the system behavior, and that will cause a runtime error. Just like our DSL, we have assertion. I remember I mentioned that if the system returns a wrong depth, we can also detect it. Does that answer your question?
There any other questions while the next speaker sets up? All right, let's thank the speaker again.